Welcome back to another Daishinfinity video. In this video, we're going to talk about the proof of the expected value theorem. Now, the expected value theorem is a very common theorem known in a lot of statistics or even probability questions. So let's first talk about what expected value even actually means. Now, normally, if we talk about probability, we are going to draw a graph and then, plot the points on it. So we first have x1 for the first input, the x2 for the second input, and x3 and the xi's all the way up to xi. Now, for each input, we also have an output, which will give us all the probabilities that can happen. Most of the times, it will get you a bell curve, which is also known as a normal distribution. Now, the expected value is the value of xi. Okay, let's just call it xi again, where the probability is the highest, meaning that if you do the experiment, any experiment, you can flip a coin, you can do some quantum mechanics. The expected value is just a specific point on the x-axis where you will mostly find the outcome. So the question is how we are actually calculating, or how the expected value is even calculated in the first place. So the expected value is e to the x, so it's a function e to the x, depending on the variable x, which is equal to the sum of xi. So we can multiply the x1 and the probability that x1 occurs plus x2 and times the probability that x2 occurs plus x3 times the probability that x3 occurs, and so on until xn times the probability that xn will happen. So it will just be in total the sum. Okay, so it's the sum. So e to the x, I'm going to write it small, the sum where I is going from 1 to n of the xi times p of x is equal to xi. Now, talking about the binomial theorem, talking about the binomial distribution, we know that the formula for px is equal to xi is just equal to the sum, where I is going from 1 to n of n. Oh, I'm sorry, it's not a sum, it's just one single digit. So it's going to be n over k times xi. So since we have xi, I'll put the xi over here. Xi times p to the xi. I'm making a lot of mistakes. P to the xi times 1 minus p, so the probability that it would not work, of n minus xi. And since we normally use k, because I come from Germany, we all normally use k for the variable, so it will just be n over k, n choose k, I'm sorry, times p to the k times 1 minus p to the n minus k. Now this is the formula we know, and we want to utilize this in our expected value theorem. So the expected value again is the sum where I is going from 1 to n of xi, so we're going to use k for that, and times p that k successes will work. Now px is equal to k, we know this one, so I going from 1 to n times k times n choose k times p to the k 1 minus p to the n minus k. So this is what we have gotten right now. This is how far we have come. Now the first thing we want to eliminate is the k, because the k has something to do with, and we can cancel it out with the n choose k. So n choose k is n factorial divided by k factorial times n minus k factorial. Since we have this one, we can simplify the k and the k factorial. If we would simplify it, let's take k divided by k factorial, which is the same thing as k divided by k minus 1, k minus 2 up until 1. Now you see we can cancel this k and this k out. So it will leave you with 1 at the top in the numerator. So 1 divided by k minus 1, k minus 2, k minus 3, which will also equal to the factorial of k minus 1. Now we're going to put this in again. Since it's messy, I'm going to make a new page. And we get this formula. So we can also plug this whole equation inside again. So it's the sum where I goes from 1 to n of, let's just say n factorial divided by k minus 1 factorial times n minus k factorial times p to the k times 1 minus p to the n minus k. Now, we want to concentrate on the formula again, because we know that we can reduce this whole factorial. We have 3 factorials inside a whole fraction, and we can reduce it into another something choose something form. Now, how can we do it? We know that n choose k is equal to n factorial, so we're taking this to the factorial, dividing it by this thing to the factorial, and then taking the top, minusing the bottom. And over here, if we look at it, I'm going to make a new page and show you how to do it. We have the n factorial, so we can already write the n, okay? And now we have the k minus 1. And we have to state that n minus k minus 1 should be n minus k. Does it work? Now n minus k minus 1 is n minus k plus 1. Well, n minus k is true, but we don't have the plus 1. So we have to do something about it. And the very clever thing mathematicians did at that time is to somehow bring the n factorial to a similar form like the k minus 1 factorial. The most easiest thing to do over here is to represent n as n times n minus 1 factorial divided by k minus 1 factorial times n minus k factorial. The reason why is we have similar groups of variables over here, n minus 1, k minus 1. So now if we factor out the n and put it in front of the fraction, and we write n minus 1 factorial dividing it by k minus 1 factorial n minus k factorial, we are going to say that we're going to check if n minus 1 minus k minus 1 will equal n minus k. Now let's ask us that question. So let's distribute the minus, which will give us n minus 1 minus k plus 1 is equal to, okay, let's see, the minus 1 and the plus 1 will cancel and it will give us n minus k. So since we have verified it, this can be written as n times n minus 1 choose k minus 1, which is very, very cool. So now since we have this formula, we can plug this one in again to our equation. So we have the sum where I goes from 1 to n of n times n minus 1 choose k minus 1 times p to the k times 1 minus p to the n minus k. So we have come far. Now the thing we want to do with this one is we want to recall a specific formula called the binomial theorem. The binomial theorem states that a plus b to the nth power is the same thing as the sum where I goes from 1 to n of n over I, or n choose I, times p to the ith power times 1 minus p. Oh, I'm sorry, I use p. I want to use b and a, so a to the I times b to the n minus I. So since we have the n and the I representing n minus 1, k minus 1, I is over here, which is going to be the p to the k, and the k is not k minus 1, so we have to change the k to the k minus 1 so that we have a similar kind of thing over there. So since we have this equation and we wouldn't want to represent p to the k in a form like this, p to the k minus 1. Now what should we do to multiply it to get p to the k? Well, we'll just add p to the first power. So that p to the k minus 1 times p to the 1 is the same thing as adding the exponents, which will equal to p to the k minus 1 plus 1. minus 1 plus 1 will go away and we'll get the same p to the k. That's why we can write it as the following. We are going to get the sum as k goes from 1 to n times n minus k, n minus 1, choose k minus 1, times p to the k minus 1 times 1 minus p to the n minus k. Now where does the n minus k, what does it stand for? N minus k stands for n minus 1, so n minus 1 minus k minus 1, which is n minus 1 minus k plus 1. The ones will cancel and we'll get 1 minus k. So we don't have any problem for that one, for that exponent. So now we can suddenly see a structure. We can see this one, we can see this one, and we can also see this one. This will result us into building our binomial theorem, which is also known as p plus, so a plus b, b is 1 minus p to the n minus 1 power. Okay, but since we have the n and the p still inside the sum, we're going to take it outside the sum. So, and we can take it outside the sum because it's independent of k. So we are going to have the n times p times the infinite, it's not the infinite, the finite sum where k is going from 1 to n, times n minus 1, choose k minus 1, times p to the k minus 1, times 1 minus p to the n minus k. So this one will equal the binomial theorem. So 1 plus 1 minus p, I'm sorry, it's p plus 1 minus p to the n minus 1. Now what is p plus 1? P plus 1 is p plus 1. P plus 1 minus p minus p will equal 0. So we will get n times p times 1 to the n minus 1 power. Now since n is not infinity, it will never equal another number. That's why it will keep going on being 1, which will mean that it will be n times p times 1, and 1 times apple is the apple itself, so we get n times p. So we have proven this formula right now in this moment, and we have proven that e to the x is equal to n times p. Very, very easy formula. Which just means that if you want to find the expected value, we just multiply the amounts of tries we had and multiply it by the general probability that it takes for it to succeed. So I hope you enjoyed this video. Please like and subscribe, follow and share this video to other people if you want to. And we'll see us in the next Daishinfinity video. See ya.